18. Hardware and virtual machines. By the end of this chapter, you should be able to show understanding of reduced instruction set computers. The initials of these are taken as RISC, and complex instruction set computers, CISC processors. The initials of these two systems are taken RISC, reduced instruction set computers, and complex instruction set computers. Right now, I will make it easy for you to remember these ISC are the same. What is it? Instruction set computers for both. Only the R and the C changes. R is for reduced, C is for complex. And you will understand the importance and the use of pipelining and registers in RISC, a thing called pipelining in executing instructions. And they are in RISC processors. Show awareness of the 4 basic computer architectures, that is SISD, SIMD, MISD, MIMD, 4 types. Of course, the words will come later. This is only the abbreviation. Show understanding of the characteristics of massively parallel computers. Very interesting. They are called server farms, also coming under that. Google, it's a very large server farm. And understand the concept of a virtual machine. Virtual machine. Not real, but almost real. The control unit. Where do you get the control unit? You get the control unit. U. And where is the CPU? Here is the CPU. There are different types, different number of pins. These are pins. In each pin, there is a signal going in to the motherboard. This is fixed to the motherboard. It is the responsibility of the control unit within the CPU to ensure that each machine instruction is handled correctly. So there are machines. All our programs will be converted to the machine code instructions. That is zeros and ones. And the control unit will look after that part, identifying what it is, and fetching, decoding, and executing. You'll learn that later. All that to be done correctly. There are 2 methods by which a control unit can be designed to allow it to perform its function. What are the 2 methods? Built as a logic circuit, electronic circuit, and with logic in it. You know about logic circuits already. So that will be hardware to control these or handle these instructions coming through these pins. Second method is microprogramming. That is firmware. Right? Hardware and the firmware. CU, that is control unit, contains a ROM component. You know already what ROM is, read-only memory. A component, that type of component is there, storing micro instructions or microcode. Another term is microcode for microprogramming. That is firmware. 1802, CISC and RISC processors. Instruction set architecture concerned with the instruction set. First the instruction set, then the instruction format. So there's a set of instructions in a particular format. The addressing modes, how do you address them? How do you store them and access them? Where are the addresses of these instructions? The addressing modes. The registers accessible by instructions. There are registers, as you know, inside the CPU, special purpose, general purpose. So how do you access them? By instructions. First take the CISC, the complex instruction set computer. In the early days, that means it came first, RISC came second, RISC. In the early days, it made the writing of a compiler for a high-level language easier. This type of computer made it easier. This instruction set complex. A single instruction, I have put them in green, so note carefully, can be more complex and involve more loading of data from memory. So from the memory, the data should come into the registers, and a single instruction, it's more complex and more loading of data. Whereas the reduced instruction set computer that came in the late 1970s, this was considered to be a better option. So first this was good, now this became better. And now compare. A single instruction is simpler. Here more complex. As the word says, complex instruction set computer is complex. And here it is simpler, requiring minimal loading of data from memory. So obviously it's better. Let's go through these definitions again. CISC is a single instruction can be more complex and involve more loading of data from memory. Whereas RISC, a single instruction is simpler, requiring minimal loading of data from memory. Features, let's look at the features. RISC on the left side, CISC on the right side, and I have bold-faced the terms which are related to this. Reduced. Fewer means reduced. And here, more. It's complex. Instructions are here and there are more. And also, it's simpler. There, it's complex. Here, it's small number of instruction formats and many instruction formats. Single cycle instructions whenever possible. In the RISC, whenever possible, it's single. But in the CISC, multiple cycle instructions, always. Fixed length instruction. The instruction is fixed length. What is the length? Is it millimeters, centimeters? No, the number of bytes or bits. Number of bits or bytes. Then here it's variable. So that alone is complex, no? To identify, we don't know the length, variable, it changes. Here, only load and store instructions to address memory. RISC only to load and store instructions to address memory. Whereas in the CISC, many types of instructions to address memory. Then fewer addressing modes. Fewer addressing modes. There are more addressing modes. And here multiple register sets, here fewer registers. Why did I put it in red? Because all these in one pattern. But here the fewer has gone to this side. You expect the fewer to be on this side. If you're going on the English meanings. So don't get mixed up. Multiple register sets are there. Here it's fewer registers. Hardwired control unit. Hardwired control unit means hardware. Yeah? The control unit here. And the control unit here is microprogram. That is firmware. And here you get pipelining easier. In the RISC, pipelining is easier. You don't know what pipelining is as yet, but we'll be learning it soon. Here its pipelining is more difficult. Now let's see what this is. The following are some points to note. The RISC, the RISC, the term reduced effects affects more than just the number of instructions. So the term reduce is just not just the reduction of number of instructions. A reduction in the number of instructions is not the major driving force for the use of RISC. Then the reduction in the complexity of the instruction is a key feature of RISC. Yes. So the number of instructions reduced as well as the complexity is also reduced. Then the typical CISC architecture contains many specialized instructions. Again, we are going to, if you consider this CISC, many specialized instructions. So complex. The specialized instructions designed to match the requirement of a high-level programming language. So the purpose, now you know the purpose. That is to match the requirement of a high-level programming language. The specialized instructions. Again, the specialized instructions require multiple memory accesses multiple times. Just one access is not enough, which are very slow compared with register accesses. Now see the difference. Where I have boldface, you have to look a second time. Memory accesses, register accesses. Memory accesses means the RAM. It's outside the CPU, whereas the registers are inside the CPU. So which is faster? This is faster. To access RAM takes a little bit more time than the registers which are already in. The simplicity of the instructions for a RISC processor allows data to be stored in registers and manipulated in them with no resource to memory access other than that necessary for initial loading and possible final storing. What is that? The simplicity of the instructions for a RISC processor allows data to be stored in register. So store in register inside the CPU and manipulated in them. You do any calculations and all that there with no resource to memory access. Without access in the memory, do it inside the register other than that necessary for initial loading and final storing. So to initially load from RAM and also to store. That is all to use the memory for. The instruction for RISC processor allows data to be stored in registers and manipulated in them. So let's see, this is RAM. This is RAM and this is CPU. And in the RAM, there's an instruction A equals 10. So there's a variable A here with the value 10. Then what you have to do is A equals A plus 1 or add 1 to A. So you can't do it there. In the RAM, you can't do it. So this is initial loading to the register, which is accumulated. General purpose register, accumulator, ACC. Right? So memory accesses which are very in registers, right? So you store it in register first, then manipulate it. What is the manipulation? Now ACC equals 10 will do that. So it is there. Then A equals A plus 1. That means 10. The moment it's 10 plus 1, it becomes 11. And then final storing. Initial loading and possible final storing. Only for these red lines I have put, the RAM is accessed. Otherwise, the manipulation is going on inside this register very fast. So then this 10 is replaced with this 11, the answer. Okay. Now, the next, the simplicity of RISC instructions make it easier to use hard wiring inside the control unit. So, because it's easy for hard wiring. The hard wiring is the logic circuits. The complexity of many of the CISC instructions makes hard wiring much more difficult. It's very difficult because the more complex it is, the circuits become complex. So microprogramming is the norm. The normal thing done is microprogramming. Now we are coming to a very interesting and important point. Pipeline. Pipeline. Nice name. It is a form of parallelism. Parallelism. Going in parallel. Applied specifically to instruction execution. So how do you remember how an instruction is executed? First, you fetch, then it is decoded, and finally executed. 3 stages in this, right? 3 stages in the breakdown of the tasks. But this cycle can be separated into a number of stages. So if you take a 5-stage model, this is a 5-stage model, right? And at the beginning, here you have this clock cycles, 1, 2, 3, 4, 5, 6, 7. 7 clock cycles. We'll see why it is necessary. Then the stages are instruction fetch, instruction decode, operand fetch, as an operand also. Then instruction execute, that is what to do, multiply or whatever do, right? Instruction execute. Then result write back. The initial, the storing final answer, that is that. To implement pipelining for a 5-stage model, the processor should have 5 independent units, with each handling one of the 5 stages identified. Right? Now, usually, if the first instruction is this, it's broken into 5 stages, 1.1, like that. So, in the first clock cycle, you know that all the actions take place according to that cycle, the tick, like the conductor conducting the orchestra. According to that, all must play. The same way, so if it was done 1.1, 1.2, 1.3, 1.4, 1.5 done. Then at this stage, the second instruction 2.1 will enter here. When this is the last stage here, it goes off, then this becomes free. The pipe becomes free and then it will enter here 2.1. So then we go on like that. But in this method, what happens is different. Right? You have 5. Now this one is handling only this, what is this? 5 independent units, like CU, like control units. Now there are units here. This unit is handling only 1.1, 2.1, that stage. Second one will handle only this stage. That's why RISC has many register sets. Each processor unit having its own set of registers. At clock cycle 6, this is a clock cycle 6, the first instruction has left the pipeline. This is one instruction, 1.5, finished. The last stage of instruction 2 is being handled. 2.4, no, 2.5 is being handled in 6. And instruction 6 has just entered. 6 also has entered. Without the pipeline, the processing time would be 5 times longer. How this happens? First of all, the instruction comes the first stage of the first instruction. Then what happens? It goes to the after that is done. After instruction fetch is done, goes to the second stage. Then what happens here? This is empty now. There's a vacancy. It's vacant. Then what happens? An instruction enters there. Because this is not now done. 1.1 is done and finished. Now in the 1.2 stage, then this can enter. When this is finished, it will go to the next stage. In the next clock cycle, the second stage of the second instruction also is taking place now, and therefore making it enabling the third instruction to enter. So then goes on like that, 1.3, 1.4. Then the second instruction, the next stage, third instruction, the next stage, the fourth instruction enters, and the last instruction, last stage of the first instruction. And these are all advancing one stage. Then it vanishes. The 1.5 is finished now. Then the second one, that second one, even the second instruction is finished. Third instruction, the last stage has come. And likewise, each one is advancing. So by this time, almost 3 have finished. Whereas if you did only 1 and then started second one, you need about 5 times that. No? One after the other. That is, this becomes 5 times quicker. Without the pipeline, without this kind of pipeline processing, time would be 5 times longer. Our idea of using the CPU, the units and handling them. Then what about interrupt handling at this point? Now the interrupts are also coming, signals coming into it while the instructions are being carried out. In the pipeline system described above, there will be 5 instructions in the pipeline when an interrupt occurs. There are 5. So one option for handling the interrupt is to erase the pipeline contents for the latest 4 instructions to have entered. Keep the current one, finish it, and the last 4 erase. Then the normal interrupt handling routine can be applied to the remaining instructions. So interrupt can be handled and then as a new instruction. And then the other option is to, now when the interrupt is finished, then you resume. Resume where you stop. The other option is to construct the individual units in the processor with individual program count registers. Remember PC program counters? So they will have separate, the numbers are their addresses. This option allows current data to be stored for all of the instructions in the pipeline while the interrupt is handled, like bookmarking. The basic computer architectures. Let's take the SISD. Now the name, single instruction stream, single data stream. If you take the abbreviation, the initial single instruction is SI. Stream, single data stream. So this stream is not taken. This stream and this stream, the initials don't count. Okay? 1, 2, 3, 4. 4 words. And single instruction, that is SI, single data, second SD. That is just to make it easy to remember. Typical arrangement in early computers and earliest microprocessors, purely sequential with no parallelism. Just one job at a time, one thing at a time. How do you explain that? SISD, sequential processing of array elements, is an array and you have to multiply this. The array element values are 4, 3, 2, 1. To multiply this, you should get 8642, no? Double of this, 8642. How is it carried out? After the first instruction, this is the initial array with 4 elements. After the first instruction, that is multiplied by 2, this 1 becomes 2. This 1 multiplied by 2 becomes 2. That's all. 432, the others remain the same. For that, for the second bit, you have to go to the second round. Then 2 multiplied by 2 will become 4. And 3 becomes 6. And final digit multiplied by 2 will become 8. All right. That is the way done one by one at a time. What about this? Parallel. Single instruction, okay? Single instruction, but multiple data stream. Multiple data stream. There is only one here single data stream. You can't overtake and go. You have to go one behind the other. Okay, what happens is one instruction is to multiply by 2. But just at the same time, 4 is multiplied by 2, 3 is multiplied by 2, 2, 1. So say at the same time you get the answer. 4 operations at the same time. SIMD, multiple. Then also schematic representation of the SIMD architecture, that same thing. What happened here? Handled by what it is, PU, processor unit, separate units. So for these 4, these are data. Data is here. For each one operation, there is a unit. Schematic representation of the SIMD architecture. SISD is single instruction stream, single data stream, a single processor accessing one memory. So that we saw, single processor. SIMD also single instruction stream, multiple data stream. Processing of parallel data input. We saw that parallelism. Requiring one control unit instructing multiple processing units. So PU, we saw 4 PUs there. No? Multiple processing units. Of parallel data input requiring one control unit. There is one control unit, but instructing multiple processing units. MISD, it's not existing at any. Multiple instruction stream, single data stream. So now you know the M and S, no? M for multiple, S for single. It's easy if you think like that. Does not exist in a single architecture. So it has to be a complex one. And in a single one, you don't get it. And MIMD, multiple instruction stream, multiple data stream. Multiple processors asynchronously processing parallel data input. Multiple instructions, single data stream, MISD. MISD is not evidenced in any individual computer. One example where the approach could be implemented would be in a fault-tolerant system. What is fault-tolerant system? What is a fault-tolerant system? To continue operating without interruption when one or more of its components fail. So this is not limited to MISD or a CPU. It's a general term, fault-tolerant system. Any other machine even, you can have it. What happens is, just because one component fails, the whole operation will not come to a halt. You can continue operating without interruption when one or more of its components fail. That is what you call fault-tolerant system. So naturally, parallelism, you can, if there is one member disabled, the other members can compensate, help it, something like that. The same data stream could be fed into 2 or more processors. So there is another possibility. The same data stream could be fed into 2 or more processors. The output would only be accepted if the same output was produced by all of the processors. So if they are matching only, it will be accepted. Otherwise, there's a error. Then MIMD. The MIMD architecture is similar to that for the type of SIMD. Similar to SIMD architecture shown in figure 18.04, with more than one processing unit receiving the parallel data streams. The difference is that each processing unit does not execute the same instruction. The multiple data stream can be provided by a suitably partitioned single memory. Each processing unit might have a dedicated cache memory. So this single memory is partitioned and given to each process, each channel, each stream. Then you get massive parallel computer system. The MIMD architecture, the last one, can be implemented in multi-computer systems, mini computers, known as massively parallel computers. Massively parallel computers. So you and I don't get them at home, right? Obviously. These are the systems used by large organizations for computations involving highly complex mathematical processing. They are the latest type of supercomputer. Supercomputer, the latest one is this MIMD system, massively parallel computer systems. The major difference in architecture is that instead of having a bus structure to support multiple processors, there is a network infrastructure to support multiple computer units. So usually we have the bus structure to transfer data, control, instructions, and all those things. But here it's a network infrastructure to support multiple computer units. The programs running on the different computers can communicate by passing messages using the network. So it's like a network all in one. An alternative type of multi-computer system is cluster computing using PCs, right? An alternative type of multi-computer system is cluster computing. Cluster is also a lot of computers together, a lot of things together. In a general term is cluster is that. Sometimes referred to as a server farm, like a farm. Farm, you get many animals, fish, or whatever. No? Here you get many servers. So can you see the picture? All these work together as one processor. Not one, but multiple, but working as one because they are working in parallel. Whenever the technology used, these systems have an extremely large number of individual processors working in parallel. That is what I say. Large number of processors, but working in parallel, like one, like a team. Team also like that. Then the virtual machine. A virtual machine is software, not hardware. Okay. Strange, no? Machine, which is software and all, usually we think machine is physical. So, but this is virtual, Virtual is what? Almost real. Not real, but almost real. The most usual type of virtual machine is the system virtual machine. System virtual machine, which is software that emulates the hardware of a real computer system. The software is pretending and showing the user that this is another machine. Looks like the real hardware of a real computer system. System virtual machine, the emulation of computer system hardware using software. So virtual machine is like pretending to be a physical one. Then system virtual machine is the operating system, the software, right? System hardware. The emulation of computer system hardware using software. Again, the emulation of computer system hardware, but using software. Remember that when a virtual machine is not being used, an application program requires support from an operating system in order for the program to run on the hardware. The principle of a virtual machine is that a process interacts directly with a software interface provided by an operating system. So that's interesting to note, right? The logical structure for the operation of a system virtual machine is shown here. Let's look at it. The hardware is there. The machine that you have, it has the host OS, operating system. So you have the host OS here. Then on top of that, you put some software, virtual machine implementation software. This is the main actor. Main actor is the virtual machine implementation software. Without that, you can't do anything. So hardware, the host OS, the original OS. Then there is software with which you can make two machines virtual. So for that, this is the virtual machine 1, virtual machine 2. This side the 2, VM2, the VM1. First the machine, then the OS, the guest OS. This is a host OS, host and guest, somebody coming from outside is the guest. So there's the guest OS for VM1, guest OS for VM2, and all the applications that you need to operate. Application program for virtual machine VM1 is there. Application program for virtual machine VM2 are there. So two machines working side by side on one machine, inside one machine. The following points should be noted when looking at figure 18.01. The application programs are installed with the assistance of a guest OS. The application programs, where are they? Right on top. The application that you use, they have to be installed with the assistance of a guest OS. That is this stage. This guest OS will support the running application by interacting with the virtual machine as though it were the hardware that the guest OS would normally run on. This guest OS will make use of the physical machine, as if the machine is here. We don't know. The user doesn't know. The virtual machine implementation software can be considered to be a utility program, can be a utility, which when running is supported by the particular host OS, by this on the OS, which is specific to the host hardware. This is specific to the host hardware, but there can be a utility program running here, making use of this. Thirdly, there can be application programs running at the same time directly on the host hardware under the control of the host OS. So here also there are applications running, and also here under the host OS also directly there can be applications running. The main advantage of the virtual machine approach is that more than one different operating system can be made available on one computer system. So you can have Windows. You can have Windows as the OS. You can have Ubuntu or some Linux program, Linux derivative. Like that, you can have two. This is particularly valuable if an organization has legacy systems and wishes to continue to use the old software, but does not wish to keep the old hardware. Legacy systems mean old ones. They are not being supported now and developed legacy, but you were using earlier. That software might need a particular hardware, particular type of hardware. That is, imagine the old hardware that they were using. Now the hardware is broken, cannot be repaired, not supported. You have to throw it. Then what do you do? With the new machine, you have to emulate that old hardware. How interesting it is. No? So without using the new software, using the old software, use the old software, but not the old hardware. You have thrown the old hardware, new hardware. Usually the new hardware and the new OS will not support this legacy system, but through this method, make it a virtual machine, like imitating the old machine. Alternatively, the same operating system can be made available many times by companies with large mainframe computers that offer server consolidation facility. So you can have many, instead of having many computers, have one computer, very large computer, and separate them like many machines, many virtual machines. So what is server consolidation facility? Server consolidation is an approach to the efficient usage of computer server resources in order to reduce the total number of servers or server locations that an organization requires. So you did not have, like, for example, if a company has 10 departments, you did not have 10 computers. You have one large computer and have them. On that same one machine, you have 10 virtual machines, each one for each department. Different companies can be offered their own virtual machine running as a server. It's very interesting, isn't it? But one drawback to using a virtual machine is the time and effort required for implementation. It's not so easy. Easy, of course, the diagram. But looking at the diagram, you can imagine this is the normal one, host hardware and the host OS. Then you have to implement this first of all. Then on top of that, you have to implement this, create a virtual machine. On top of that, you have to install, like these two are like these two. This virtual machine, this is a physical machine. On the physical machine, you have the host OS. On the virtual machine, you have the guest OS, virtual machine OS. On top of that, you have to install like Word, Excel, and all that, the application software. So initially, it's very difficult. One drawback to using a virtual machine is the time and effort required for implementation. Another drawback is the fact that implementation will not offer the same level of performance that would be obtained on a normal system. A normal system, the physical one, will act, let's say, at X, rate of X, the speed, performance. When you make it work like two machines, the Y, the rate of Y will be less than X. The performance will be degraded. Performance will be less, lower than the original physical one. That is a disadvantage. So there are two disadvantages. No? One drawback is the difficulty in implementation. The other one is it becomes slow. Naturally, no? One person doing two jobs. The Java virtual machine discussed in chapter 8 is an example of a process virtual machine. It's a process virtual machine based on a different underlying concept. You can't really call it as physical. The process virtual machine provides a platform-independent programming environment that allows the program to execute in the same way on any platform. This is specific software that only supports running a Java program. That you must realize. The Java, JVM, Java Virtual Machine, JVM, that will run only Java. Whereas what we were talking about, the virtual machine, you can implement many other compatible software, of course, compatible on that OS. There are Mac OS handling applications which cannot be implemented on a Windows OS. Likewise here, The Java is only for Java. This is specific software that only supports running a Java program. A system virtual machine supports any application. We were looking at a system virtual machine. Remember? System virtual machine. So that explains the whole process of the virtual machine. And what have we learned? What have we learned in this chapter? Control unit can be hardwired or microprogrammed. Remember, hardwired or microprogrammed. Hardwired is logic circuits, electronic circuits, and microprogrammed is a ROM component having the instructions. Risk. Processors have a number of advantages compared to CISC. Yes, we saw many advantages. Pipelining is one of the reasons for choosing a RISC architecture. Right? So pipelining also we saw. Parallelism can be based at the instruction level, processor level, or computer level. A system virtual machine is software emulating hardware, like imitating. The Java virtual machine is an example of a process virtual machine. That is the end of this chapter. Hope you learned a lot in this and you will complete the assignments